Hello everyone, and thanks for joining this episode of tinyML Talk. My name is Gianmarco Iodice. I'm the chair of the tinyML Global Meetups, and today I have the pleasure to moderate this talk where Swapnil, Sayan, Saha, an algorithm development engineer from STMicroelectronics, we talk about physics-aware auto-tiny machine learning. Before we start with the presentation, I'm gonna just give an introduction. I'm gonna present a few slides concerning the tinyML Foundation. First of all, I want to thank on behalf of the tinyML Foundation all our partners which are behind this incredible adventure, incredible work behind the tinyML. So in particular, I'd like to thank AHC, Arduino, ARM, BrainChip, Agentpulse, Embed UR, Efficient, Greenwaves Technologies, Gravity Inc., HiMax, ImageMob, Infineon, Innaterra, Not AI, NXP, PNG, PIMIC, Pauling Technology, Corbo, Qualcomm, Renesas, Knight Electric, SensiML, Sony, Silicon Labs, STMicroelectronics, Synaptics, Synchance, and TDK. So thanks again, because it's because of our partners that we are here. We are also having these events, tinyML events, which are most of them also free for all of you in order to share the knowledge about tinyML. In terms of where to learn more, where to join this community, you can join the tinyML community on Meetup. We have more than 19,000 people already there with their register. And we also have physical meetups in 49. We have 49 physical groups, meetup groups in 41 countries. But the community is not only on Meetup, is also on other platforms, including on LinkedIn, where we have around 4K members and over 14 followers. So don't forget to register to be always aware of the latest initiatives, events around tinyML. So one thing I want to remind is the YouTube channel, the tinyML YouTube channel. So this is the right place to learn more about this technology, where we host all the presentations, not just the tinyML talks, but also other events organized by the tinyML Foundation. So here there are many videos concerning technical and also business related talks. Of different kinds. So if you haven't registered, I really recommend, because this is the perfect place also to start. If you don't know anything on tinyML, this is the right place where you can find also introductory material for that. Well, the tinyML Summit is approaching very fast. This is a physical event that we're gonna have on the 22nd of April to the 24th of April. So if you haven't registered yet, please do it, because also this year will be a very incredible event. Also an opportunity to meet the leaders and the experts in this field in person, and also have connections for your tinyML related work activities. So the tinyML Awards is another initiative of the tinyML Foundation. So where we are going to nominate the best product on the and the best prototype and the Sustainable Future Pioneer Award. So this is another crucial event. There is a QR code that you can use the app to go straight to the URL. So if you haven't downloaded yet, this is a report that I highly recommend, because this report has been prepared by the leaders in this field and the experts to give an overview about the technologies that are suitable for tinyML. This will give you an overview, for instance, of the software stacks or the hardware and the other technologies that are making possible machine learning at the very edge. So on devices that not necessarily have internet connection. With my pleasure, I'd like to introduce Swapnil Sayan Saha, who is an algorithm development engineer at STMicroelectronics. So he received his PhD and master degree in electrical and computer engineering from the University of California, Los Angeles in 2023 and 2021, respectively. He also holds a bachelor's degree in electrical and electronic engineering from the University of Dhaka in 2019. His research explores how rich, robust, and complex inference can be made from sensors on board low-level embedded system within tight resource budget in a platform-aware fashion. To date, he has published more than 25 peer-reviewed articles and patents and received more than 30 awards in robotics, technical, and business case forums worldwide. So it is a pleasure to introduce. I'm looking forward to learning from you. So it's your turn. Yeah, thanks a lot.
Yeah, thanks a lot, Gianmarco, for the introduction, and thanks to everyone for attending. So, as Gianmarco has already said, the topic of today's talk is physics-aware auto-tiny machine learning. So, as part of the tiny machine learning community, I want to give a huge thanks to all of the hardworking academics and the industry folks who have worked so hard to bring tiny machine learning into a reality. So now we see like tiny machine learning almost everywhere. So as we know, tiny machine learning, it consists of a combination of hardware and software that allows us to do always-on, ultra-low power, and on-device data analytics. And since its inception, almost a decade back, we have now been able to deploy tiny machine learning almost everywhere. Like we see tiny machine learning being used for wildlife tracking in the ocean, where there might not be any sort of internet or network connectivity available, but we're still able to make extremely complex and fine-grained behavioral inferences about these animals. We're now putting tiny machine learning into picosatellites as well, where we're using tinyML to stabilize how the picosatellite is orbiting around the Earth. We're using tiny machine learning for cases where you have to make decisions within split seconds and where there would be a lot of latency if you would offload the machine learning tasks to the cloud. For example, when we are flying these micro-aerial vehicles, or as we call them, drones, they have to make very split-second decisions in order to make agile movements. So tiny machine learning has helped a lot in that domain as well. And recently, we have started putting tiny machine learning into things that don't even have a battery. For example, we must have heard about energy harvesting systems, which try to harvest ambient energy from the environment. So for detecting, certain events, such as, when person is walking into the room or not, we're now starting to put tiny machine learning into these battery-less systems as well. So in summary, tinyML has enabled us to realize applications where we would need to make complex inferences, but where we would not be able to probably upload, such raw sensor data to the cloud and wait for the inferences. So this would not have been possible without all of the hard work that, all of you have done. So what we call tinyML, I'd like to refer to it as first generation efforts, and we mostly focused on how we can actually squeeze all of these, big neural networks within the resource bounds of these small tinyML platforms. So as you know that these platforms that typically have just a few megabytes of flash and a few kilobytes of RAM. So most of our time initially was focused on how we can, fit machine learning models, which we designed for the cloud or gateways, into these tiny devices. So with that, we are now facing a few challenges in the tinyML domain. And the first challenge is how we can make such systems obey what we humans refer to as physics or rules or constraints. So suppose that you want to, land a quadrotor on its own, and you want to use a tinyML model for that. So in this simulation, what I did was I trained a machine learning model to try to control the quadrotor and land it. So as you can see, the machine learning model was quite successful in landing the quadrotor, but in the process, it also managed to crash the quadrotor as well. And the reason it happened is because the machine learning model, it did not have any notion of what safety was. So its only goal was to just land the quadrature, and it did that successfully, but in the process it also damaged the quadrature. So another scenario happens when we are doing something known as complex event processing. So you might have a sequence of different human activities that you want to recognize, and those human activities must follow one after the other. For example, if you have a nurse who is going to perform a sequence of actions such as administering food and then administering injection, before administering food the nurse should wash hands. But if a machine learning model is not able to detect this sequence of actions one after the other, then it would result in what we refer to as invalid sanitary protocol. So since we're deploying these tiny machine learning models at the edge, physics matters a lot more, since the actions that are being taken by this tiny machine learning model, they're closer to us. And it has been shown numerous times that if you are not careful, then standalone neural networks, they will not be able to ensure that they're going to obey all the expected rules and physics of the underlying system. So in order to solve that, what machine learning engineers do is deploy additional routines, which is known as symbolic programs. So these are things that try to control how the output of the machine learning program looks like. You can think of them, kind of like if-else statements, like, oh, if the, training data, or if the sensor data has some features, then probably we should not trust the machine learning model that much, and probably we should just hardcode some value, to be outputted by the neural network. But once you start, inputting, all of these additional routines, it puts a burden on the underlying embedded system too. Because now, not only do you need to fit the neural network within the resource bounds of the embedded system, but you would also have to fit this additional symbolic logic within the resource limits as well. And typically, when we are trying to deploy these neural networks or machine learning models within embedded systems, we use something known as parameter tuning or neural architecture search. Once you start bringing in symbolic routines, then you'd be greeted with mixed and discontinuous search spaces, and that's not really good when you're trying to do neural architecture search, because not a lot of search algorithms can deal with mixed or discontinuous parameter spaces. Your cost function might become arbitrary as well. Normally in NAS, we try to optimize the memory, the accuracy, and energy, but now you'd have additional terms coming in. For example, you might have terms such as adversarial robustness, or terms such as, following a certain physics functions. And you would also have to deal with more runtime faults due to more moving parts. So deploying a machine learning model in embedded systems, as if it was not complicated enough, now you have additional code that's running in parallel with the embedded system, with the neural network. So the synergy between the neural network and the symbolic code, it results in more complicated code, and you might have more, syntax errors or more runtime errors if you are not really careful. And finally, when we are doing neural architecture search, we tend to model, the memory, the accuracy, and energy using some form of analytical functions that people have discovered in the past. But now this problem is more open-ended, right? Since you can have any arbitrary logic on board, you cannot really have proper proxy for the memory uses of your neural network program anymore. So in summary, finding the optimal synergy between the neural and symbolic components within the tight resource constraints of embedded systems is extremely challenging. And that's where I present the concept, which I refer to as neurosymbolic auto tiny machine learning. So as you can see, there are lots of different words here. So neurosymbolic, it consists of two words, neural and symbolic. So a neural simply refers to a machine learning model that's running on board, and symbolic refers to some form of human interpretable logic that is also running on board. And in order to find the most appropriate architecture of the neurosymbolic program that fits on board, we propose what is known as neurosymbolic architecture search. And to automate this whole process, using some form of programs that can automatically compile, the program from a high-level language to the deployment code and automatically do the architecture search for you without you having to write any code. So what is neurosymbolic artificial intelligence? Very simply speaking, it's a program that contains a machine learning model and some form of human readable code that operates concurrently with the machine learning model. So think of a micro-aerial vehicle that's flying and that's trying to detect objects on the ground. So normally you would use machine learning models such as YOLO or some form of, lightweight version of it on board. So why do you use neural networks for this? It's because we found out that neural networks are more performant than symbolic models for object detection. They're non-parametric, so it's very easy to scale them to different kinds of object detection problems without a lot of retraining. And neural networks are quite robust against noise and any form of domain changes that might be around. On the flip side, we have something known as symbolic programs. So you can think of a symbolic program, for example, in case of an aerial vehicle as optical flow, where the aerial vehicle's camera is trying to detect the intensity of pixels around it, and using some physics or mathematical formula, it's trying to make the aerial vehicle navigate. So this form of machine learning is interpretable since we know the equations and the maths around such formulations. They're data efficient, so you don't really need a lot of training data to get a sense of if the program is valid or not. And this is what we call physics and context aware, since it knows like how the processes in the environment evolve with very strict mathematics. It's aware of the constraints and physics in the underlying system. So neurosymbolic AI, its goal is to combine the best from both worlds. So if we combine, for example, aerial object detection with optical flow, we get what we refer to as a self-navigating surveillance coordinator. Now, the next topic is neural architecture search. So historically, we have used neural architecture search to automatically find us the most performant neural architecture from a space of some machine learning operators within some sort of platform constraints. So in neural architecture search, what we have firstly is a search space where we can have different kinds of machine learning operators. For example, if we have like CNN operators, we can have the size of kernels, the number of layers of the CNN, the type of activation functions to use, and so forth. Then we have something known as an optimization function, which guides the search algorithm to try to minimize or maximize some form of nonlinear program. So mostly in NAS, what we try to do is we try to optimize some form of linear combination of memory uses, accuracy, and energy. And then we have the search algorithm itself, whose job is to construct a machine learning model from the search space, get a score from the optimization function by evaluating that candidate model, and then repeating this process multiple times until it finds the most performant model that has the highest accuracy, but at the same time that fits within the resource bounds of the tinyML platform. So in this talk, we're going to focus mostly on the search algorithm and optimization function in the first part of the talk. So to do neurosymbolic architecture search, as I have said earlier, we have a few challenges, like the parameter space can be mixed or discontinuous. The optimization function formulation can be arbitrary. So it's an extremely open-ended problem. So we pick a search algorithm that can help us make this open-ended problem as tractable as possible. So we adopt what is known as black box Bayesian optimization to do neurosymbolic architecture search. And what we'll show is that this optimizer, it can efficiently handle mixed and discontinuous search spaces extremely easily. So in Bayesian optimization, there are two components. The first component is referred to as a surrogate function, and the second component is referred to as an acquisition function. So the goal of a surrogate function is to approximate the optimization function with respect to the search space. So if you look at this equation, we have what we refer to as the symbol omega. So omega is your search space. So as I said, it can have different kinds of machine learning operators, different kinds of, I would say, neurosymbolic program atoms, and so forth. And in our case, we use a Gaussian process to do this approximation for us. And the reason we use a Gaussian process is because it doesn't need a lot of training data in order to model this optimization function extremely well. So what we call it in technical terms is, under data scarcity, it's able to provide tractable assessment of uncertainty. And Gaussian process is a non-parametric model, so you don't really have to worry about the shape of your optimization function with respect to the search space. So we are using a non-parametric model with mean mu and a method kernel function k over the search space omega. And the next component is the acquisition function. So the goal of the acquisition function is to select the next neurosymbolic program to sample and evaluate at each step in the neural architecture search formulation. So we use Monte Carlo sampling with upper confidence bound, which has an adaptive exploration factor beta. So if you look at the equation for the acquisition function, you can see that there are two terms. The first term, it refers to the goodness of the sample point, which we call exploitation. The second term is referred to as the uncertainty of the sample point, which is referred to as exploration. So if you have heard about reinforcement learning, we know in multi-arm bandits problems, we have this whole exploration exploitation concept, where in one epoch of our bandit problem, we try to reuse experience from the past in order to select the best sample that we have found out so far. And in the next epoch of the bandit problem, we select a point that we have never sampled before. So we do that so that our neurosymbolic architecture problem, it does not get stuck in a local optima. And there are some analysis that we've done in our paper. You can take a look at the paper later. We found out that if we have this form of exploration and exploitation with this adaptive exploitation factor, with almost 90% theoretical guarantee, you will be able to find near optimal values at the boundary of violating deployability constraints. So what do I mean by that? So when you are doing neural architecture search, you might have models whose accuracy is linearly proportional to the memory uses, but then suddenly you will have models that no longer fit within your device at all. Normally, a gradient-driven NAS formulation is going to smooth out anything across those boundaries, but then it might as well give you neural programs or neurosymbolic programs that do not fit within the resource bounds of your tinyML platform. So gradient-free Bayesian optimization does not do that. So as soon as you reach that boundary, it's going to penalize the search algorithm by a huge amount, so that the search algorithm is not going to even try to give you those invalid models at all. So we're going to take a look at that graphically a little bit later. So now formulating the neurosymbolic optimization function, it looks very similar to a very generic neural architecture search problem. So what you are trying to solve is a nonlinear program with constraints. And here you can see like the usual terms that we usually see when we are doing NAS. So you have your error term, which is usually the validation loss or validation accuracy. You have measurements for your flash, RAM, and latency, and all of these are being weighed differently by the scalarizations, which we call lambda. So the goal of this optimization problem is to construct a fault-free neurosymbolic program. So what do I mean by fault-free? By fault-free, I mean a program that fits within the resource bounds of the device, but at the same time, it does not induce any form of programmatic errors. Like there should not be any runtime errors or any surprises when you're trying to run the program. And this neurosymbolic program, it should have the best possible latency and accuracy, but at the same time, it should fit within the constraints of the device. And while our search algorithm is solving this neurosymbolic optimization function, it should be careful in the sense that it does not give us the smallest neurosymbolic program every time. Like if I have a microcontroller, for example, which has a little bit more memory than another microcontroller which I was using before, it should ideally give me a bigger neurosymbolic program. It should not just give me the same neurosymbolic program every time. Now, then we have the search space sigma, which I'm going to talk about in the second part of my talk. So it has now, instead of just neural operators, it's going to have both neural and symbolic hyperparameters. So it's going to have trainable weights, the neural operators, as well as atoms, from which you can construct neurosymbolic programs. So I talked a little bit about invalid regions in the search space, and I said that in our neural architecture search formulation, we penalize our search algorithm by a huge amount when it reaches the invalid region. So this is what we refer to as hard thresholding. So in hard thresholding, as I said, what happens is that when you reach this form of invalid region, where your accuracy is slowly increasing, where your memory uses is increasing, but then the memory uses suddenly crosses that boundary where it does not fit on the device anymore. Instead of smoothing it out as gradient-driven NAS formulations would do in soft thresholding, we penalize the NAS formulation by a huge amount so that it does not venture into that space anymore. And we're able to do this because we're using a gradient-free formulation. We're using Gaussian process combined with upper confidence bound. And thanks to this GPU-CV formulation, we're able to observe the small but valid linear region where memory uses is proportional to accuracy. But at the same time, we're not crossing into the invalid region. And in order to go one step further, we do what is referred to as platform in the loop search. So we do not use any kind of analytical proxies or any sort of assumptions on what kind of program the user would deploy. We treat it as a very open-ended problem. So you are free to choose any machine learning model and any combination of symbolic program atoms that you might want to deploy. Our NAS algorithm does not really care about what problem you are deploying, because it's optimizing at the execution level. So instead of optimizing just the machine learning model at the high level, it converts that neurosymbolic program to assembly language and then runs it on the platform, or if you have a simulator, and then sees what dynamics is going on at the tinyML platform itself. And we've done some analysis and found out that if you do this sort of platform in the loop search along with hard thresholding, it's going to be 50% faster than if you used some form of assumptions about your program and if you use soft thresholding. So this is sort of like an overview of what our platform in the loop search looks like. So in our search space on the GPU server, we have our neural backbones as well as symbolic program atoms. We feed that to our search algorithm, which is all coded in Python. The search algorithm calls TensorFlow to train the model. And then it uses a neural parser to convert that model to C. And then it uses a symbolic parser to convert the symbolic portion of your program to C. And then our microcontroller, it's connected to the GPU server either as a simulator or as a real hardware in the loop. And then you get the real-time memory and latency measurements from the RTOS that's within the microcontroller that's out there. So we have done some analysis, both quantitative and qualitative. So this is, sort of like a summary of the qualitative analysis. So compared to existing neural architecture strategies, we're able to operate on mixed and arbitrary parameter spaces and optimization function terms. And since we're operating at the execution level, platform in the loop is able to guarantee deployability by taking the synergy of the neural and symbolic programs at the lowest possible level into account. And Bayesian optimization, it might not be as good as TNAS or evolutionary search algorithms or reinforcement learning, but Bayesian optimization takes the best from all of them within a small package that you can run, for example, on the local GPU machine. So you don't really have to spend a lot of money investing in, a lot of cloud servers. You can just try this out on a simple machine with, maybe 1 or 2 GPUs and then see if it works out for you or not. So we benchmarked the capability of, our NAS algorithm on the MLPerf tiny version of 0.5 inference benchmark. So one of the benchmarks we ran was CIFAR 10, and we found out that, our NAS algorithm is able to outperform the benchmark accuracy by 4.3%, and it also outperforms the baseline by almost 4.5 and 17.5%. And compared to a lot of the baselines, our NAS algorithm, since its formulation is extremely inexpensive, it converges a lot faster. And as I said earlier, if you are doing this platform in the loop formulation with hard thresholding, you're able to converge a lot faster and also able to get higher accuracy models as well. Now, one of the things that we noticed is search space is also extremely important. So if you don't know something about a problem, and if you feed like a wrong search space to your neural architecture search, then no matter how fancy your training algorithm is, you are always going to get subpar model. So most of my life I've spent analyzing inertial measurement unit data. So I'm not a person who is comfortable with, for example, audio. So once I was trying to, for example, run my NAS on audio, I was feeding it, models which I have used previously for inertial measurement units, such as temporal CNNs and 1D CNNs. And I found out that these models are not really the best when it comes to working with audio. So this is where the motivation for my search space is going to come from, that why have only one model backbone in your search space? Why cannot we have, for example, a CNN, a LSTM, a decision tree, a SVM? Why cannot we have like 10, 12 different models in the search space? And I'm going to show that in the second part of my talk. Okay, I think we are in the second part. So before I dive in, do we have any questions so far for the first part of the talk?
There is a question concerning the optimization functions. So do these optimization function inherently omit model reduction that could be seen with pruning and quantization? If so, does it mean we could be leaving out models that could have fit on the hardware without another step of model preparation before deployment?
Yeah, I did not include that in my slides for reasons of space, but if you okay, it's not in this slide also. So actually our, tinyNS is actually quantization aware. So you can have the option of including quantization within your search space as well. So if you look at this table, you can see that one of the baselines, recent baselines from ARM, it's called micro-DC. So it has pruning and quantization within its search space. So we also support, pruning and quantization as well. Yeah.
Thanks for your answer. The second question is, what are the neurosymbolic operations used?
Yeah, so I'm going to cover it in the second part of my talk. So there are, if I want to just give you a little bit brief overview, there are 5 different kinds of neurosymbolic programs. So we cover like the first 4 that you see in the slide, but I'm going to explain about this in the second part of my talk a little better.
Okay, there is another question.
Mhm.
Where and how did the physics of the problem come to the algorithm?
Yeah, so it is going to come from, so if you look at this slide, you see that there is a symbolic parameter in all of these algorithms that's working with the neural block. So as I'm going to show you, this symbolic program is going to bring in all of the physics that's going to work in parallel with the neural network.
Okay. So which pruning policy are you supporting?
So we for now support unstructured pruning that's present in the support. Yeah, like the default pruning. Yeah. So you can specify the ratio of pruning that you want to use, like what percentage of voids you want to prune. Yeah. Mhm.
Thank you. So there are no other questions.
Okay.
So actually the questions I can see here, can you please provide a link to the slides? Oh, of course. So this session is recorded, so will be available on YouTube, and the slides will be available on the tinyML website. Yes, I think we can continue with the second part of the
Sure. Yeah. Yeah, so I think the second part of the talk is more interesting because here we finally formalize the entire, physics hour tinyML formulation. So now that we have looked at, how we optimize this neurosymbolic, programs, like now that we have a good, automated architecture search based formulation, now we can finally start to use it to do what we refer to as neurosymbolic tiny machine learning. So there are 5 different kinds of neurosymbolic AI. So the first kind is referred to as symbolic neurosymbolic, where we have the raw data being first fed to a symbolic program and then being fed to a neural network. Very simple example is you can extract some features from the raw data and then you can feed it to a neural network. That's like the simplest example that I can think of. Then the second kind of program is referred to as neuro and then an arrow and then symbol. So here what you have is the neural network takes care of extracting features or some inferences from the raw data. But then the final decision is being made by a symbolic program. So you can think of this as, for example, you can have a decision tree that is working in parallel with a finite state machine. So if you have been following STMicroelectronics, we have a bunch of sensors we call as the machine learning core, where you can run decision tree and finite state machines on board. So there you can have either the decision tree or the finite state machine working independently, or you can have the decision tree and the finite state machine working together. So that is an example where you can have a neural network and then some form of symbolic program working, one after the other. And then you have something known as neuro-union compile symbolic. So here you don't really have a symbolic program that's running on board. But during the learning process of the neural network, you inject some form of regularizers to control, how the neural network behaves with respect to certain inputs. Then the fourth paradigm is referred to as symbolic, then within bracket neuro. So here you have your neural network and symbolic programs that are operating concurrently on the raw data. But then you have the output being jointly, the joint decision is being taken by either a neural or symbolic program. So you have like 2 outputs that are of the same nature that are coming from the symbolic and neural network, but then you finally fuse them using another neural network or a symbolic program. And then the fifth paradigm, which you are not going to cover, which is a little bit more recent, is you inject special layers, which you refer to as physics-aware layers within your neural network to constrain the behavior. So recently, people have come up with certain interesting layers, such as Hamiltonian neural networks, Fourier neural networks, where there are special symbolic layers that you inject within your neural network to constrain its output to follow some form of physics. So that's referred to as neuro, then within bracket symbolic. So in our talk, we're going to cover the first 4 paradigms today. So let's take a look at the first paradigm, which is symbolic neurosymbolic. So we formulate this problem as consisting of a series of independent functions that we apply on the raw data, and then we take our final decision using a single machine learning model. So if we look at our symbolic search space, what we have is referred to as a 2D hyperparameter matrix. So each row of this parameter matrix that you see, it refers to the arguments of each function that we're going to apply on the raw data. Suppose that you want to extract, I don't know, 3 features from your raw data. Suppose you want to extract the fundamental frequency, the zero crossing, and the mean from your raw data. So if you wanted to formulate the arguments of those as a 2D parameter matrix, the mean obviously is not going to have any parameters, so it's just going to be null for the row of mean. For your fundamental frequency, you might have, for example, the number of beans you want to include in your Fourier transform. So that might be a parameter for that certain function. And then for the zero crossing, you might have either positive zero crossing or negative zero crossing or some form of threshold. So those are going to be the arguments of the third row of your parameter matrix. So as you can see, this actually makes the problem extremely intractable when you have a large symbolic search space. So we actually ran this raw through our NAS algorithm, and it worked quite fine for example, 10, 12 different features operating on the raw data. But if you have like hundreds of different features that you want to extract from the data, then your search space is going to have like extremely mixed parameters, right? It's going to have categorical variables, continuous variables, conditional variables, which are fine in terms of our search algorithm, but they're going to have different ranges, and that's going to, not really work out well when you're trying to, optimize the neurosymbolic program within as few epochs as possible. So we map that into what we refer to as a slider matrix, where we formulate it as a pseudo-continuous min-max normalized argument for each of the functions that we apply on the raw data. And then our neural search space, instead of having just a single machine learning model, we have different kinds of machine learning models from which we can construct our neurosymbolic program from. For example, we can have decision trees, we can have CNNs, LSTMs, SVMs, and so forth. But in our problem formulation, since only one model can finally work on the symbolic output, we consider only one of them at each step of the NAS using an ordinal mask. So I'll show the formulation of this using 2 examples. So the first example is when we're trying to optimize features and a single backbone. So the application here is that we want to do gesture recognition, and we want to do the gesture recognition using a CNN, but we want to extract some features first. And now we don't know which of the features are the most useful or not. So here you can see that we have around 12 features in our search space, and each features are going to have their own parameters, which are going to be formulated as the 2D parameter matrix. And then once you run this through our search algorithm for different kinds of microcontrollers, you can see something very interesting happening. So the first thing that you see is that we know that feature extraction adds its own compute burden on the microcontroller. So obviously, if you extract all the features, that's going to be computationally intensive. However, the most interesting part is that our NAS, or the Neurosymbolic Architecture Search framework, it's able to pick the most important features when you don't have a lot of resource. So for gesture recognition, we know that temporal features such as peak-to-peak, the mean of the signal, as well as the Fourier transform of the signal, they're extremely important in distinguishing between various modes or classes that you might want to differentiate between. So our framework is able to find out the most important features first, and then as your microcontrollers become more and more powerful, it starts to add more redundant features in order to improve the accuracy. And if you look at the model size versus accuracy plot on the right-hand side, you can see that when you don't have a lot of memory to work with, it's picking a small model. But as you have more and more resources available, to play with, it picks bigger and bigger model, and it also picks more features as well. The next example is you are trying to do gesture recognition, but you don't know which model works best for this problem. So here in our problem, we have 5 different models in our search space. So we have a temporal CNN, we have 2 kinds of specialized RNNs, we have a decision tree called Bonsai, and we have a KNN, which we call ProtoNN. And we tell the search algorithm to give us the best model among all of these 5 different backbones. And as you can see, if we have just stuck with simple CNN, which is referred to as TCN, we would not have gotten the best possible accuracy and the lowest possible model size that we would have achieved, for example, with FastDNN. So when you have multiple models in your search space and you want to do gesture recognition, we found out that you can get models that are 98 to 740x smaller, yet they are 3 to 6% more accurate for doing human activity detection. And you can get even more, you can go more tiny. For example, if you're trying to do fall detection, we found out that you can just get away with a model whose footprint is less than 2 kilobytes. So this is where I bring the importance of having open-ended problems. So instead of having, just a single backbone, just a single, symbolic paradigm, why don't we treat it as a more open-ended problem and have like multiple copies of this? So at least we're able to, get an idea of what works best for us. So the next formulation is referred to as a symbolic program that's operating at the output of the neural network. So you can have like two formulations for this. You can have either a single function that's operating at the output of the neural network, or you can have something known as a program graph. So what is a program graph? So if you have a collection of logical, relational, arithmetic, and conditional operators, you can create something known as a decision tree out of this collection of operators. So you can think of a decision tree as a collection of if-else statements. So at each node, it's trying to, make a decision based on what has happened, in the past or not. And then ultimately, if you are able to synthesize, multiple copies of the decision tree, then your search algorithm simply becomes, finding, selecting one of these trees, because what essentially happens is you can synthesize multiple of these trees using tree enumeration algorithm, and ultimately you want to just select one of these trees that you have already created, or you can construct these trees using this search space as well during your neurosymbolic optimization problem. Like whichever path you want to take, that's fine. So an example of this, suppose that you already have synthesized a tree. So an example of this might be that suppose you have a object detection model such as YOLO that's detecting several humans within a video, and then you are using, for example, a Kalman filter to track the detected humans across multiple frames. So you already know the formulation of your decision tree. It's a Kalman filter, but now you want to optimize the hyperparameters of it. So you can do that jointly using our neurosymbolic problem. So you can jointly optimize the parameters of the neural network as well as that of the Kalman filter. So here in the table, what you see is that if you look at the handcrafted model versus what we get from the 250 megabyte limit model, you can see that their performance is quite similar. But the handcrafted model, it took the human a long time to tune. Like the human had to try out randomly different parameters, and then based on some experience, the human had to hand tune that model. But you don't really have to do that if you use our neurosymbolic architecture search formulation. You just give it the platform you want to deploy it on, and it's going to automatically tune the neurosymbolic program for you within just a few GPU days, compared to, you might spend as well as hundreds of human hours to tune this program using hand. So you no longer have to do that. Then we have what we refer to as neuro-union compiled symbolic. So here we have a single machine learning model operating on the raw data. We do not have any symbolic part running on the embedded system, but we have these symbolic rules that are expressed as part of the learning algorithm. We can do that in two ways. The first way is very simple. You add more terms to your optimization function. So the base formulation, if we remember, it had error, flash, RAM, and latency. But you can now add additional parameters. For example, you can add adversarial robustness to your parameter. You can add, like other parameters to it. For example, the energy consumption of your model. If you have an energy harvesting system, you can add parameters that have to deal with the timing or deadlines of when, your program needs to finish a certain task or not. So those things you can add as, additional terms in a NAS optimization function. The other thing you can do, you can add something known as a physics metadata channel as additional inputs to the model. So rather than just feeding raw data to your model, why don't you add, some form of physics formulation in order to try and constrain the output of the neural network? So if we take a look at the second formulation, so we apply it to a problem known as neural-inertial navigation. So in neural-inertial navigation, the goal is to find out where you are based on just your IMU data. So, those who are from navigation, we typically refer to this as a data reckoning problem. And we know that one of the challenges here is that, inertial measurement units, they tend to drift a lot over time. So people have tried to solve it using neural networks, and they've found out that neural networks work quite well in this regards, but neural networks still have a few problems. So one of the problems that people noticed is that if you just stand in one place and if you don't walk, but if you just, for example, rotate your body, then the neural network is going to still give you some position outputs. Now we know that, of course, that is invalid, right? Because you are not really taking any translational steps. So what we did was we started feeding step counter data or step detector data to our neural network. So we feed it through what we refer to as a physics metadata module. And what the step detector was doing was it was providing additional latent information about whether valid translational movements were happening or not. So once we feed this physics-aware neural-inertial navigation and combine it with lightweight model backbones in our search space, and give it like some form of constraints, like okay, we want to deploy it on this microcontroller. Then what we found out is that compared to all of the other baselines, even like the classical baselines such as Kalman filters, we're getting navigation models that were almost 31 to 134x smaller, yet they had higher resolution. So this gives you again yet another sort of proof that the power of physics-aware inertial navigation. That without physics, you would have gotten models that might or might not follow physics, but whose size has to be quite big. But once you combine physics with this whole architecture search framework, then you get these tiny machine learning models which are aware of the physics around them, but still which has like better error characteristics. The final formulation I'm going to talk about today, it's referred to as a symbolic neuro problem formulation. So here what we have is we have a neural network and a symbolic program that are jointly operating on a bunch of sensors and giving you the same output, but now you have to somehow fuse the outputs of both. And to do that, we use Kalman filter theory. So we think of a neural network as a noisy system model of the world that we're operating on. And we think of a symbolic program as noisy measurement updates. Now, how do we fuse them using a Kalman filter? So the first thing that we do is we know that a Kalman filter has two steps, a Kalman propagate step and a Kalman update step. And in a Kalman propagate step, we have our system model, which we are using to update the system when we are not having measurements. And then we also have the Lyapunov function, which we are using to propagate the state of uncertainty forward. So in the system model, we separate the neural and non-neural parts. So ultimately what happens is your neural network is providing a black box mapping between your sensor data and your states. And then you have a linear part as well, which is also updating the states finally. And then in the Lyapunov function, we know that it's used to update the covariance matrix or the state of uncertainty forward. So here, what we do is we treat the evolution of our sensor data with respect to the states as the Jacobian of the neural network. So we are computing the gradients of the neural network onboard the microcontroller and just using it to update the covariance matrix. So an application of this is known as neural-Kalman filtering, or neural-Kalman inertial navigation combined with GPS. So we have our neural-inertial navigation model that we shown in the previous slides as our system model. Obviously, we also have the physics metadata module to make it aware of the physics. And then we have the GPS, which is providing additional inputs to this Kalman filter during the measurement update step. So when you combine the velocity of the neural-inertial navigation model with the location and velocity of the GPS measurement model, and you feed it all through a Kalman filter, you get the position of the robot, for example, operating in a field. So we use this, in an agricultural setting. So we were tracking agricultural robots using neural-inertial navigation and GPS. And one of the advantages of this is that you no longer have to model the dynamics of the robot. So typically, if you ask robotics engineers or mechanical engineers, like how do we model a navigation problem, the first thing they're going to say is, oh, give me the model of the robot. So you don't have to worry about that anymore because the neural network takes care of modeling, the dynamics of the robot for you. And what we found out is that once you put all of this in a navigation setting, our neural Kalman filter, it actually outperforms all the existing navigation algorithms, such as extended Kalman filter, uncentered Kalman filter, and it also even outperforms, if you just use GPS. So one interesting thing that we found out, due to space constraints, I've not added it to the slide, when you looked at the trajectory plots, is that the neural Kalman filter, it was combining the short-term accuracy and smoothness of neural networks. So we know that inertial measurement units in navigation settings, they do quite well in the short term, but they start to drift in the long term. So what our neural Kalman filter did was that in the short term, it put more trust on the neural network, but in the long term, it was putting more trust on the noisy GPS or GNSS updates. And it was able to do all of this using under 1 megabyte of memory for an ARM Cortex-M4 microcontroller. So let's conclude. So what we have seen is that neurosymbolic tiny machine learning, this is a new paradigm that we're proposing. So it's able to enable context-aware, physics-aware, robust, interpretable, and performant edge AI systems. You are now able to follow certain rules, certain constraints that you want to impose on your system through it. And we are automating this whole process using this neurosymbolic architecture search framework, which we refer to as tinyNS, which can, automatically parse these high-level programs in Python to see for you, deploy it onto your target embedded system, and then see like what the memory latency is, what the different kinds of errors your neurosymbolic program yields at the edge. And we have seen a broad spectrum of new applications, such as, for example, doing fault detection on chip under 2 kilobytes of memory, using neural-Kalman filters within a microcontroller. Then we have seen how we can do inertial navigation within microcontrollers. We have seen how we can do gesture recognition within AirPods and so forth. So if you want to try tinyNS, you can visit this link. So this was part of my doctoral work. Here are like some of the funding agencies. And if you want to try out Neurosymbolic, AI within, a product offering. So ST, as I said, has a bunch of sensors that allows you to run neural networks, machine learning models, as well as symbolic programs directly within the sensor. So now you don't need even microcontrollers anymore. You can do all of this within the sensor itself. So with that, I conclude. Jian, the floor is all yours. And if we have any more questions, I think now we can take.
Absolutely. So thanks a lot for your insightful talk and presentation. Quite a lot of technical details presented today. So let me go to the questions that we have in the Q&A tab. So one of these is about, do we have to write separate machine learning model for getting the feature, for getting the feature importance, or there is some inbuilt function?
So for the feature extraction problem, if I can go to that slide. So for this, no, you don't have to write any, feature selection algorithms, to get the most important features. The tinyNS is going to do that for you. If you want to, you can. That will be provided as an additional input to tinyNS, but we did not see the need for that.
So the other questions, how do you gain from pruning in inference and mapping the network?
Yeah, so yeah, I mean, if you prune the network, as we know, it's going to obviously result in memory savings, right? So once you are, pruning away the unintended weights, you are going to get a neural network that is lighter. So we don't prune like all the neural networks. We provide it as part of the search space. So our search space also has quantization and pruning as an option. So if our neurosymbolic architecture search algorithm feels that it might need to prune the network to get memory savings, it is going to do that for you.
Done. So how does tinyML Edge AI compares with building the machine learning model in MATLAB, Simulink, and embedding those in embedding firmware program? Is a more generic, actually, but generic question.
Yeah. So, I mean, I'm not just going to talk about MATLAB Simulink. I mean, if you look at like any, for example, AutoML, tinyML workflow, typically you start with, collecting some data, picking your neural network models. If you are extracting features, you pick the features out of them. Then you train the model. You do post-training quantization if it's a neural network. If it's not a neural network, then you just convert the model to C, and then you try to deploy it. Problem is that there is a lot going on as an application developer on your side, right? So you have to make sure that the model you are picking it's the best that's going to operate on the data that you have, right? So that is not guaranteed for a lot of problems. You are in charge of picking the hyperparameters of your model. So that's another burden that you have. You are in charge of converting the model to C, although now there are a lot of programs that do that for you. For example, if you give an example of MATLAB Simulink, it converts your model from MATLAB to C for you if you give it a microcontroller model. So you don't have to do any of that if we use, for example, an AutoML framework like tinyNS. So you just feed it the data. You just, formulate the optimization function, then it does all of these things for you. So you can think of it as, more automated and more geared towards, more generic problems where you might not have, a starting domain expertise to start with. So as I gave you the example, like I'm not the best, when it comes to audio because I've never worked with audio data. And I fed it a very bad model backbone, which, always worked for me for IMU data, but it failed miserably for audio. So in those kind of problems, you might want to, do some exploration, right? So tinyNS allows you to do that kind of exploration, like what model is best for me, like what are the hyperparameters that's most suited for my application, what are the best set of features that's most suited for my application. So it takes away that burden from you of selecting the parameters and allows you more flexibility to work on the data. So this is another thing I want to talk about. The data, I think, is the most important when it comes to any machine learning problem. Like you can throw bad data at tinyNS. tinyNS will obviously fail, right? Any machine learning model will fail if your data is bad. So what tinyNS is doing, it's removing that model engineering effort from your side and asking you to focus more on the data curation, data processing, data engineering, and those kind of things. Yeah.
Thanks a lot. So rather than rely on GPS to take over for long-term drift, could you use it to recalibrate the neural algorithm and continue its use?
Yes, we actually do that. So in the long term, what we do is that so no matter what IMU you use, and no matter even if you use a very fancy system model, even if it's a neural network, it will drift eventually over time, and it is going to become unusable. So after a few minutes, what we do is that we reset the neural network. So whatever output the neural network has given in terms of the position, we completely override that using the GPS. So we do that kind of calibration. Yes.
Nice. Thanks. So what was the GitHub link? Do you have a GitHub link? Yep.
Yeah.
Exactly. So yes, I saw it in the last slide. So let's wait just a few seconds to give anyone to take note. But remember that the slides anyway will be available on our website, and also the video of the recording will be available on YouTube channel. Perfect. So what type of framework exists for development integration with use case specific chipsets that could provide feature data?
Yeah. So I mean, in terms of, I don't know about a lot of, I don't know about tinyNS. I'm going to talk about the ones that are commercially available. So model integration, I think the first product that comes to my mind, which I first ever used, was Edge Impulse. That's a really good platform that you might want to start with. If you want to play around, integrating your model on board. Then ST has a bunch of tools. So we have what we recently released as MEM Studio. I don't have it in the slide. So MEM Studio allows you to do things that are very similar to what tinyNS allows you to do. So in MEM Studio, you just feed the label data. With a single click of a button, you can get a machine learning model that fits within one of our, inertial measurement units or MEM sensors that have the integrated machine learning core or intelligence sensor processing unit. So you can try out MEM Studio, that is available on st.com. Then there is NanoEdge AI as well, which is from ST. So that is also an AutoML platform. So you don't really have to write any code for that if you want to do the model integration at the edge. But I guess for model integration, I think what you are referring to is more of a, I guess, lifecycle kind of thing, that you have already integrated your model on the edge device and now you want to do the testing. So for that, I'm not really aware of any of the platform. I know that at ST internally, we're working on a platform on that, which has like this whole notion of model lifecycle that's going on instead of just doing the AutoML part. But you can start out using the kind of tools that I have mentioned to try this out, and of course you can use tinyNS as well. Yeah.
Thanks for your answer. So how long does the optimization process take?
Okay, so this obviously depends on the problem that you are trying to solve. So I can talk about the benchmark that we did on MLPerf. So here what you can see is that, for example, for CIFAR 10, it took 3 GPU days to optimize for an ARM Cortex M4 microcontroller. And if we take a look at this problem, where we're trying to optimize yellow and Kalman filter, here also it took around 3 GPU days. So in our problems, we have not seen tinyNS take more than a week. And it was all being done in the machine with 2 GPUs. So if you have, for example, 100 iterations you want to run for tinyNS, it should not take you more than it should take you anywhere from 2 to 7 days, I would say. But obviously, it depends on the scale of your problem. If your search space is extremely complicated, you might want to run tinyNS for more iterations. So that might take a little bit of more time. But generally, Bayesian optimization, it was, when it was designed to take the best out of reinforcement learning, evolutionary algorithms, and gradient-driven algorithms. So we know that reinforcement learning and evolutionary algorithms, they are extremely good in terms of giving you the best possible model, but their convergence time is very high. And then gradient-driven NAS, their convergence time is extremely low, but then they're not able to operate effectively on mixed and discontinuous parameter spaces. So Bayesian optimization sort of came out as a compromise in order to provide the best out of both worlds. So you should expect Bayesian optimization to have a convergence time that's somewhere, in between gradient driven and, that of RL and evolutionary algorithms. But yeah, I mean, if you want a specific number, it never took us more than a week for our convergence.
So one of the attendees was saying whether you could write the tools you mentioned earlier about the feature with the feature extraction mechanism. So probably you can follow up on the tinyML meetup forum. You can probably write there some of these tools that might be beneficial for some of the attendees.
Mm-hmm.
Yeah. So we are approaching the end of the hour. I think we have almost addressed all the questions. There is only the last one. So does symbolic regression SR useful in the embedded system?
I mean, you can think of it as, one form of neurosymbolic paradigm. I would probably put it in the first paradigm that I talked about. If I go back my slides. So among the 5 paradigms, if you think of symbolic regression, you can sort of think of it as, mostly within the first paradigm, right? So you can have symbolic regression as operating on the raw data, giving you some form of outputs, and then you are using a neural network to make the final inference. So yes, definitely you can use, symbolic regression also, within one of these paradigms as well. Yeah.
So we have finished with the Q&A session. So on behalf of the tinyML Foundation, I want to thank you again for the very detailed and well-prepared presentation. I think given also the level of questions and the number of questions received today, it was absolutely a very good presentation. So thanks again on behalf of the tinyML Foundation. So we're approaching the end of this episode. And before we leave, I want to thank again our strategic partners that are behind this event, and also many others in person and virtually. So in particular, I want to thank the executive strategic partners, Qualcomm, Synchant, the platinum strategic partners, which are Embed UR, Sony, the gold strategic partners, which are ARM, Agimpulse, Infineon, Innaterra, Renesas, STMicroelectronics, Synaptics, and all these silver strategic partners listed here, which are 8zip, Arduino, BrainChip, Efficient, Green Waves Technologies, Gravity, HiMax, ImageMob, Not.ai, NXP, PNG, PMIC, Palin Technology, Corvo, Schneider Electric, SensiML, Silicon Labs, and TDK. And with this slide, which is related to the copyright notice, I leave you for today. It was really a pleasure to moderate this talk. I really enjoy it. And I wish you to welcome you again to the next episode of tinyML Talks. Bye-bye, and thanks again for watching this episode.